Hello everyone, I'm Professor Chia-Po Wei. If you need any assistance or want to contact me, you can write me emails. Course information such as slides, videos, or dates of examination will be posted both on the announcement board of Cyber University and our course website. I still use remote teaching, and the pre-recorded lecture will be available in English. If time allows, the lecture videos in Chinese are also provided. A week quiz will start from Monday 8:30 a.m. Please remember to log in Cyber University. If you have any questions after watching the videos, you can use the TA hours. The teaching assistants will answer your question. The location is at the EC building of A011-2. In this week, we will learn section 3.6, row space and column space. Given a matrix A, you will learn how to compute its row space, its column space, as well as the null space. We will also discuss the solvability of linear equations in terms of these subspaces. In fact, you can prove the row space, the column space, and the null space are subspaces of a vector space. And in section 5.2, we will learn the concept of orthogonality. In particular, the column space is perpendicular to the null space of A transpose. You need to familiarize yourself with these definitions of row space and the column space and null space. Otherwise, you will encounter difficulties when learning section 5.2. In this slide, I will give the definition of row space and column space, which is in page 173 of the textbook. Let A be an m times n matrix, which means A has m rows and n columns. The row space of A is the collection of vectors. The vectors are the linear combination of the row vectors of A. Because each row vector is in R1 times n, and therefore the row space of A is a subspace in R1 times n. Next, we define the column space. The column space of A is the collection of the linear combination of columns vectors. Since each column vector is in Rn, so the column space is a subspace in Rn. The column space is also called the range space and is denoted by Ra. Here, R stands for range and R does not stand for row, so Ra means the range space or the column space. Some textbooks use a different definition of row space. Some textbooks will denote the row space as Ra transpose. Ra transpose is the column space of A transpose, and this definition is different from the one defined in our textbook. To see why, first I denote the row space as row A for ease of presentation. Note that this notation is created by me, and our textbook does not have this notation. For this notation, we know that row A is a subspace in R1 times n, while the Ra transpose is a subspace of Rn. Note that the vector space in which the the subspace lines are different. Row A is in R1 times n, while RA transpose is in Rn. In this slide, I will rephrase the definition of column space in terms of the mathematical language. Recall that the column space is the collection of the linear combinations of column vectors of A, and the column space is also called the range space, which is denoted as Ra. We know that a linear combination of column vectors of A can be expressed as x1a1 plus x2a2 up to xn an. Here, a1, a2, an are column vectors of A, and x1, x2 to xn are the coefficients. So the term ax is actually the linear combination of column vectors for some x. Therefore, we can rephrase the definition of Ra as the set. Here, we use the brace to denote a set, the set of B in Rm, such that B can be expressed as Ax for some x in Rn. This is the definition, the precise definition of Ra in terms of the mathematical language. We will use this definition many times when we want to prove something regarding the column space. So you need to familiarize yourself with this kind of definition. In particular, in section 5.2, we will encounter this definition many times. I will use example 1 to illustrate the row space. Let A be a matrix in R2 times 3. The row space of A is the set of all three tuples of the form alpha times the first row plus beta times the second row. And this is the linear combination of row vectors of A for some alpha beta. We know that the vector addition is closed in the row space, and also the scalar multiplication is closed in row space. Therefore, the row space of A is a subspace. And since each row is in R1 times 3, so the row space of A is a subspace in R1 times 3. You can verify that 1, 0, 0 and 0, 1, 0, the two rows forms a basis of the row space of A. To do this, you have to prove the two rows are linearly independent, and you have to prove the two rows span the row space. Since the basis has two vectors, so the dimension of the row space is 2. But for other examples, the basis might not be obvious as in this example. So to determine the dimension of the row space, first we need to find a basis of the row space. In the next slide, we will see this can be achieved using the row operations. After the basis is found, the dimension of the row space is the number of vectors in the basis. Next, I will prove Theorem 3.6.1, which states that two row equivalent matrices have the same row space. Before giving the proof, let's see what we can do with this result. Let U be the row echelon form of A. Then the matrices U and A are row equivalent, since U is formed from A by a finite sequence of row operations. Therefore, U and A are row equivalent. Then, in view of Theorem 3.6.1, we know that the row space of U and A are the same, so we have row A equals row B. And know that the non-zero rows of U will form a basis of row A. Remark 1 provides a way to compute the row space of A. To compute the row space A, first we compute the row echelon form of A. Then the non-zero rows of U will form a basis of the row space of A. Next, we give the definition of rank of a matrix. The rank of matrix A is the dimension of the row space of A. We will use the notation rank A to denote the rank. And by this definition, we know rank A equals the dimension of row A. From remark 1, we know that to compute rank A, first we reduce A to its row echelon form U. Then rank A is the dimension of row A and also the dimension of row U, which is the number of non-zero rows of U. Next, let's see the proof of Theorem 3.6.1. Suppose B is row equivalent to A. This means that B can be formed from A by a finite sequence of row operations. Therefore, the row vectors of B must be linear combinations of the row vectors of A. Hence, we have shown that row B is a subset of row A because the row vectors of B must be linear combinations of row vectors of A. By the same reasoning, we can also show that if A is row equivalent to B, then row A is a subset of row B. Because of the two inclusion, because row B is a subset of row A, and we also have row A is a subset of row B. Therefore, we can conclude that the two row spaces are in fact equivalent, the same. Therefore, we have proved row B equals row A. In this slide, I will use example 2 to illustrate row space and rank. Let A be a given matrix, and our goal is to compute its row space and rank. To do this, let's reduce A to the row echelon form, and we obtain the matrix U. U is the row echelon form of A. We know that the only non-zero rows are the first two rows of U. Hence, the first two rows of U form a basis for the row space of U. Since A and U has the same row space, therefore this basis is also the basis for the row space of A. Hence, the row space of A is the set of all three tuples of the form alpha times the first row plus beta times the second row. And to find the rank of A, we know that by definition, rank A equals the dimension of row A, which equals the dimension of row U. And since the basis for the row space of U has two vectors, therefore the dimension of row U is 2, and this is the rank of A. I will use example 1 to illustrate the column space and also illustrates the relationship between RA transpose and the row A. Let A be a given matrix in R2 times 3, and our goal is to compute the column space of A, which is denoted by RA. By definition, RA is the set of all vectors of the form alpha times the first column plus beta times the second column plus gamma times the third column. Because RA is the set of all linear combinations of column vectors of A, and we know that the column space of A is a subspace of R2 because each column of A is in R2. Next, we discussed the relationship between RA transpose and row A. We know that RA transpose is a subspace of Rn because each column of A transpose is in Rn, and the row space of A is a subspace of R1 times n because each row of A is in R1 times n. For example 1, row A is the set of all vectors of the form alpha times the first row plus beta times the second row, while RA transpose is the set of all vectors of the form alpha times the first column of A transpose plus beta times the second column of A transpose. In fact, you can prove that if Y belongs to RA transpose, if and only if Y transpose belongs to row A. Next, we will revisit the null space, the definition of null space, which is in page 138 of the textbook. Let A be an M times n matrix, and the null space NA denote the set of all solutions to the homogeneous system AX equals 0. That is, NA is the set of vectors X in Rn such that AX equals the 0 matrix. NA is called the null space of A, and we define the nullity of A to be the dimension of the null space of A. Next, we show how to compute the null space of A. We know that A can be written as matrix E times matrix U, where U is the row echelon form of A and E is a non-singular matrix. And actually, E represents a set of row operations. To compute the null space, we need to solve the equation AX equals 0. Now we substitute A with EU into A, then we obtained EUX equals 0. Since E is a non-singular matrix, EUX equals 0 holds if and only if UX equals 0. This means that if X is a solution to UX equals 0, then X must also be a solution to AX equals 0. Therefore, we have shown that ax equals 0 and ux equals 0 have the same solution set. Therefore, we can solve ux equals 0 to find a basis of the null space of A. To compute the null space of A first, the first step is to compute the row echelon form of U. Then we solve ux equals 0. And then we will obtain a basis for the null space of an A for the null space of A. Next, I will discuss the solvability of linear equations and its relationship with the column space. Given a linear equation AX equals B, where A is an m times n matrix. Here, m is the number of equations, and n is the number of variables to be solved. X is in Rn, which is the variable to be solved, and is denoted by x1, x2, up to xn. The vector b is an Rn. Vector b is a given vector. We can rewrite the linear equation in the vector form, which is x1a1 plus x2a2 plus up to xn equals b. Here, a1, a2, up to an are column vectors of matrix A, and x1, x2, up to xn are the variables we want to solve. Given the linear equation in vector form, we can then discuss the solvability of linear equation from this expression. From the linear equation in vector form, we know that if the linear equation ax equals b is consistent, then there exists x1, x2, up to xn satisfying the linear equation, which means b can be written as a linear combination of column vectors of matrix A. And this means B is in the column space of A. On the other hand, if we have B is in the column space of A, then B can be written as a linear combination of column vectors of A. So there exists x1, x2 up to xn, such that x1a1 plus x2a2 plus up to xn equals vector b. And this means x is the solution to the linear equation ax equals b. Therefore, we have proved the linear equation ax equals b is consistent if and only if B is in the column space of A. From system equations in vector form, we have proved that a linear system AX equals B is consistent if and only if B is in the column space of A. This result is the Theorem 3.6.2, also known as the consistency theorem for linear systems. And in fact, Theorem 3.6.2 is a restatement of the Theorem 1.3.1, which is a result you have already learned in Chapter 1. Next, let's consider the homogeneous equation AX equals the zero vector. This equation is a special case of the linear equation Ax equals b by setting the vector b as the zero vector. We can use Theorem 3.6.2 to infer that Ax equals 0 always have a solution, because the zero vector is always in the column space of A. Why? Why the zero vector is in the column space of A? This is because the column space of A is a subspace, and the subspace always contains the zero vector. Hence, the homogeneous solution Ax equals 0 always have a solution. And it is easy to see that x equals the zero vector is always a solution of the homogeneous equation, because a times the zero vector equals the zero vector, and we called x equals the zero vector as the trivial solution. If Ax equals 0 has a non-trivial solution, this means there exists some non-zero x, some zero vector x, which means x1, x2 up to xn not all 0. If there exists some non-zero x satisfy x1 a1 plus x2 a2 plus up to xn an equals 0, then this means a1 a2 up to an are linearly dependent. This is the definition of linear dependency. Hence, if the homogeneous has a non-trivial solution, if and only if the column vectors of A are linearly dependent. And if A1, A2 up to AN are linearly independent, then the equation x1 a1 plus x2 a2 plus up to xn an equals 0 only has the solution, the zero vector. That is, the homogeneous equation Ax equals 0 only has the trivial solution if the column vectors of A are linearly independent. Let's prove Theorem 3.6.3, which is a very important result when we want to analyze the solvability of linear equations. Theorem 3.6.3 has two statements. The first statement states that the linear systems Ax equals b is consistent for every b in Rm, if and only if the column vectors of A span Rm. I will call the first condition as condition A, and the second condition as condition B. The first statement has two parts, the if part and the only if part. To prove the only if part, we assume condition A holds, and our goal is to prove that condition B holds. Now suppose we have the linear system Ax equals b is consistent for every b in Rm. This means every b in Rm must be in the range space of A, because if we do not have this result, then there exists some vector b not in Ra. Then by Theorem 3.6.2, Ax equals b is not consistent. then we arrive at a contradiction, since condition A says that the linear system is consistent for every b, but we have found some b not in Ra such that AXB is not consistent. So um, every b in Rm must be in the range space of A, and this in turn means that uh, Rm is a subset of the range space. And since Rm is a subset of the range space of A, then we have the column vectors of A span Rm. Next, we prove the if part. The if part assumes that condition B holds, and our goal is to prove that condition A holds. Now suppose the column vectors of A span Rm. Then this condition means that Rm is a subset of the range space of A. Hence, every b in Rm is also in the range space of A. Then since b is in the range space of A, then we know that the linear equation is consistent for every b in Rm, and the proof is finished. We know that without the condition Rm is a subset of Ra, then we cannot say every b in Rm is also in the range space of A. So without the condition Rm is a subset of Ra, we cannot say the linear equation is consistent for every b in Rm. Next, we prove the if part. The if part assumes that the column vectors of A are linearly independent, and our goal is to show that the linear equation has at most one solution for every b in Rm. We know that the column vectors of A are linearly independent, implies that Ax equals 0 has only the trivial solution. Later, we will use this condition. Now suppose x1 and x2 were both solutions to Ax equals b. We will show that x must equals x2. To see this, we verify that x1 minus x2 must be a solution to the homogeneous equation Ax equals 0, because if we multiply matrix A with x1 minus x2, then we have Ax1 minus Ax2, where Ax1 is b, because x1 is a solution of the linear equation, and x2 is also a solution to the linear equation. Hence, we have b minus b equals the 0 vector. Therefore, we have showed that x1 minus x2 is a solution to Ax equals 0. Notice that we have Ax equals 0 only has the trivial solution, and hence x1 minus x2 must be the trivial solution, the 0 vector, and hence x1 equals x2. We have shown that if there exist two solutions to the linear equation, then the two solutions must be unique. Thus, we have proved that the linear system has at most one solution for every b in Rm, and the proof is finished. Let A be an m times n matrix. We know that by definition, the range space of A is a subset of Rm, because every column vector of A is in Rm. This implies that the dimension of the column space is less than or equal to m. Now, if we have the condition that the column vectors of A span Rm, then n is greater than or equal to m. Because if the number of column vectors of A is less than m, then they cannot span Rm. If the column vectors of A are linearly independent, we will have n is less than or equal to m, because every set of more than m vectors in Rm is linearly dependent. If the column vectors of A form a basis for Rm, this means the column vectors are both span Rm and are linearly independent. Hence, the two inequalities n is greater or equal to m and n is less than or equal to m both need to be satisfied, and therefore we have n mass equals m. We also have the corollary 3.6.4, and n times m matrix is non-singular if and only if the column vectors of A form a basis for Rn. You can prove this by yourself. Next, I will use example 3 to illustrate how to compute basis for row space and null space of a given matrix A. To do this, the first step is to compute the reduced row echelon form of A, which is denoted by U. U is obtained by a sequence of row operations. You can refer to section 1.2 to find the row echelon form of A. Now we obtain the reduced row echelon form, and the first two rows are non-zero rows, and thus the first two rows form a basis for the row space of A. And the rank A is the dimension of the row space, which is 2, since the basis has 2 vectors. And the number 2 is also the non-zero rows in the reduced row echelon form. The number of non-zero rows in U is 2. Next, we compute the null space of matrix A. To compute the null space, we need to solve AX equals 0. In page 9, we have shown that AX equals 0 and UX equals 0 have the same solution set. Thus, if X satisfies UX equals 0, then X also satisfies AX equals 0. Hence, we can compute the solution to UX equals 0 to find the null space, to find a basis for the null space of matrix A. Now we denote X as x1, x2, x3, x4. And from UX equals 0, we have 1 times x1 plus 2 times x2 plus 0 times x3 plus 3 times x4. And we have the first equation. We also have 0 times x1 plus 0 times x2 plus 1 times x3 plus 2 times x4, which leads to the second equation. The third row of U are all zeros and is of no use. And now we have 2 equations and 4 variables. So the number of freedom is 2. Let's denote x2 as alpha and x4 as beta. Alpha and beta are two freedoms. After substituting x2 and x4 into the two equations, we obtain x1 equals minus 2 alpha minus 3 beta, and x2 is alpha, x3 is minus 2 beta, and x4 is beta. So the solution to the null space can be written as alpha times a vector plus beta times another vector. Now the two vectors are actually forms a basis of the null space. The null space has two freedoms, and therefore the dimension of the null space is 2. The dimension of a null space is also called the nullity of A. We know that for this example we have nullity A plus rank A equals 4. 4 is the number of columns of A, and this result is a very well-known result, which is the rank nullity theorem. And we will prove this theorem in Theorem 3.6.5. Next, we prove the rank nullity theorem. Let A be an m times n matrix. Then we have rank A plus nullity A equals n, where n is the number of columns of A. Let U be the reduced row echelon form of A. We know AX equals 0 if and only if UX equals 0. That is, the solution set of the two equations are the same. If A has rank R, then U will have R non-zero rows. And UX equals 0 will involve R lead variables and n minus R free variables. To see this, we will use the previous example to illustrate. In this example, the reduced row echelon form of A is U. In this example, we know rank A is 2, and therefore there are two non-zero rows in U. There are corresponding to two lead variables. The two lead variables corresponding to two equations. Now we have 4 variables. Now the number of variables is the number of columns of A, and the freedom is n minus R, where R is rank A. In this example, n minus R is 2, so the number of freedom is 2. And thus, the dimension of NA will equal the number of free variables, which is n minus R. Therefore, rank A plus nullity A is R times n minus R, which equals n, and n is the number of columns. Example 3 is a great example for illustrating the rank nullity theorem. Next, we will prove Theorem 3.6.6, which states that if A is an n times n matrix, then the dimension of the row space of A equals the dimension of the column space of A. That is, dimension of row A equals dimension of column space of A. Now suppose A has rank R. That is, the dimension of row A is R, and let U be the reduced row echelon form of A, and UL be the matrix obtained from U by deleting all the columns corresponding to the free variables, and delete the same columns from A and denote the new matrix by AL. I will use example 3 to illustrate this. Let U be the reduced row echelon form of A, and U is this matrix. Know that the second column and the fourth column corresponding to free variables. Thus, UL is obtained from U by delete the second column and the fourth column. Hence, UL is the first column and the third column of U. And the AL is obtained from matrix A by delete the same column. That is, delete the second column and delete the fourth column. So AL is the first column and the third column of matrix A. Since AL and UL are row equivalent, we know ALX equals 0 and ULX equals 0 have the same solution set. If you are not sure why this happens, you can refer to page 9 of the slides. We know that the columns of UL are linearly independent because we have delete columns corresponding to free variables from U. So the columns of UL are linearly independent. Because of this condition, we know X equals 0 is the only solution to ULX equals 0. And since ALX equals 0 and ULX equals 0 have the same solution set, therefore X equals 0 is the only solution to ALX equals 0. This in turn implies that the column vectors of AL are linearly independent. Because AL has R columns, and therefore the dimension of the column space is at least R. To see this, know that the definition of the column space is the collection of all linear combinations of column vector of A. So if AL has R columns, then the dimension of the column space is at least R. We have proved the dimension of the column space is greater than or equal to R. R is the dimension of the row space. So far, we have proved the dimension of the row space. So far, we have proved the dimension of the column space is greater than or equal to the dimension of the row space. We have proved that dimension of RA is greater than or equal to dimension of row A. If we replace A with A transpose, then this equality will become dimension of the column space of A transpose is greater than or equal to the dimension of the row space of A transpose. And we know that each column of the A transpose is a row vector of matrix A. Hence, dimension of RA transpose is equal to dimension of the row space of A. From a similar reasoning, since each row of the A transpose is a column of the matrix A, and we have dimension of the row space of A transpose equals the dimension of the column space of A. Now we have proved the dimension of row A is greater than or equal to the dimension of RA. And we also have the dimension of RA is greater than or equal to the dimension of row A. And in view of the two inequalities, we can conclude the dimension of row A equals the dimension of the column space of A. Because of theorem 3.6.6, we have the following remark. Rank A equals rank A transpose. To prove this, by definition, rank A is the dimension of the row space of A, which is equal to the dimension of the column space of A. This is the result of theorem 3.6.6. And the dimension of the column space A equals the dimension of the row space of A transpose. And by the definition of row space, we have the dimension of the row space of A transpose equals the rank of A transpose. Hence, we have proved rank A equals rank A transpose. This is a well-known result regarding the rank of a matrix. Example 4 illustrates how to compute a basis for the column space of a matrix. I will introduce two methods for computing a basis for the column space. Method 1, first transform A into the reduced row echelon form, and we denote the reduced row echelon form by U. We know that the leading ones occur in the first and the second column of U, and thus from U we can select the first and the second column of A to form a basis for the column space of A. And therefore, the first column of matrix A and the second column of matrix A forms a basis for the column space of A. We know that although matrix U and matrix A have the same row space, but their column space are not equal, and therefore the column space of U is not equal to the column space of A. Hence, we cannot use the column vectors from U to form a basis for the column space of A. Matrix U only tells us which columns of A to use to form a basis. In this slide, I present another method for computing a basis for the column space. To do this, first we compute the transpose of A. A transpose is this matrix. Then we compute the reduced row echelon form of A transpose, which is denoted by V. And know that the row space of A transpose equals the row space of the matrix V, since row operation will not change row space. And the V is the reduced row echelon form of A transpose. And now we have found the basis for the row space of A transpose, which are the first two rows of the matrix V. The first two rows of matrix V form a basis for the row space of A transpose. Because each row of A transpose is the transpose of each column of A, and hence the transpose of the first two row of matrix V forms a basis for the column space of A. Now I have presented two methods for computing a basis for the column space. You might ask which method to use, and my suggestion is that if your goal is to compute basis for both the row space and the column space, then you can use method 1, because they all need to compute the reduced row echelon form. From the reduced row echelon form, we can compute a basis for the row space, and we can also infer from the reduced row echelon form to obtain a basis for the column space. If your goal is to find a basis for the column space only, then I would suggest method 2, because it is more direct. The next example is exercise 11, which is in page 179 of the textbook. Let A be an m times n matrix. Prove that rank A is less than or equal to the minimum of the set n and n. We know that the dimension of the row space cannot exceed m, because matrix A has m rows. And the dimension of the column space cannot exceed n, because matrix A has n columns. Therefore, we have rank A is less than or equal to m. Since rank A equals the dimension of the row space, we also have rank A transpose is less than or equal to n, because rank A transpose is the dimension of the column space of A. In view of the above two inequalities and the condition that rank A equals rank A transpose, and this condition appears in page 18 of the slide. Because of the two inequalities and the condition rank A equals rank A transpose, we can conclude rank A is less than or equal to the minimum of the set m and n. The next example is exercise 28, which is from page 180 of the textbook. Let A be an m times n matrix, and B be an n times r matrix, and C is the product of matrix A and B. We need to prove that the following three statements hold. Statement A is that the column space of C is a subspace of the column space A. Statement B is that the row space of C is a subspace of the row space of B. And statement C is that rank C is less than or equal to the minimum of the set of rank A and rank B. This is a well-known result regarding the rank of a matrix. First, we prove statement A. If C belongs to the column space of C, then C can be written as ABX for some x in RR. This is due to the definition of the column space. You can refer to page 4 of the slides to see the definition of the column space. If we denote Bx as y, then ABX can be written as AY. Hence, C equals AY for some y in Rn. And again, by the definition of column space, we know C belongs to the column space of A. Since every vector in the column space of Rc also is in the column space of A, we conclude that RC is a subspace of the range space of A. Next, we prove statement B. If D transpose belongs to the row space of C, then D belongs to the column space of C transpose. Since each row in C is the transpose of a column of C transpose, we know C equals A times B. If we take transpose on both sides, then we have C transpose equals B transpose A transpose. And since then we can use part A. And now we have D belongs to the column space of C transpose. By part A, we know D must be in the column space of B transpose. And from this condition, we know D transpose belongs to the row space of B, since every column of B transpose is a row of the matrix B. Now we have proof if D transpose is a row of if D transpose belongs to the row space of C, then D transpose also belongs to the row space of B. Hence, we have shown row space C is a subspace of the row space B. Finally, we can prove statement C. Know that part A implies that rank C is less than or equal to rank A, because RC is a subspace of RA, while part B implies that rank C is less than or equal to rank B, because row C is a subspace of row B. And because of the two inequalities, we can conclude rank C is less than or equal to the minimum of the set rank A and rank B. This result is a well-known result regarding the rank of matrix product. We have finished section 3.6, and I have selected some exercises from section 3.6, which is in page 178 of the textbook. You can use these exercises to test whether you really understand the materials covered in this section. The answers to the selected exercises are given in the next few slides. I only provide the answers, and you need to fill in the details of the proofs or computations. After learning section 3.6, given a matrix A, you should be able to compute the row space, the column space, as well as the null space of matrix A. And you also need to familiarize yourself with Theorem 3.6.3. And you don't need to memorize the proof of the theorem, but you should understand the statement of the Theorem 3.6.3. You should be able to use this theorem to analyze the solvability of linear equations, such as to determine whether a linear equation is consistent or not, or such as to determine whether the linear equation has exactly one solution or has infinitely many solutions. And the Theorem 3.6.3 and also the Theorem 3.6.5 are two well-known results for analyzing the solvability of linear equations. Feel free to leave comments regarding the video or the slides. If you have question, you have if you have question, you can use the TA hours, or you can write emails to me. Or if you need any other assistance, you can also write email to me. I hope the video provides you a better understanding of the row space and the column space of a matrix A.